Hello, ladies and gentlemen. My name is Nate Nishidora, and welcome to another webinar presented by Phillips Lighting University. This webinar is titled Adaptive Lighting for Exterior Applications, and is presented to you by Michael Siminovitch.
Hello, everybody. Thank you very much for coming this morning for my presentation on adaptive lighting. I'm going to take this opportunity to talk about adaptive lighting from a conceptual background, but also relative to some of the work that we're doing here in California with the codes and standards process. So I'm going to really look at this from a conceptual standpoint and also technical demonstration, and then getting into some of the codes and standards efforts. So my name is Michael Siminovitch. I'm the Rosenfeld Chair in Energy Efficiency here in California. Also a professor at UC Davis, and I teach undergraduate and graduate courses in lighting. And I'm the director of the California Lighting Technology Center. Just in terms of just a little bit of background, I direct a lighting technology center here at UC Davis, which was established as a industry, state, university partnership, public-private partnership, engaged broadly in research and development issues here in California. Just in terms of background, we do principally four things. We do research and development of new lighting technologies, always in partnership with the industry. We're very engaged in lighting demonstrations where we're relighting municipalities, schools, colleges, etc. We have a very broad education and training program, both at an undergraduate level, but we're also very engaged with the lighting profession, teaching classes to architects and contractors. We're also very engaged in the building codes and policy work, where we take a lot of the R&D work that we're doing and help in the codes and standards enhancement programs, where we're developing new standards for buildings. Again, research and development is a big part of what we do. We're very engaged with partnerships between the state institutions and the lighting industry, really looking at trying to seed new technologies and new ideas into best practices for the lighting of buildings. I'm very active with a lot of the commission's work. I was one of the co-authors on the strategic lighting plan, which looked at some very bold types of vision for energy savings, but also looked at strategic opportunities. And I think adaptive lighting is really one of the cornerstones of the key policy work that California is focusing in on now. Very engaged in the standards process, worked very hard as a collaborative with the industry on the 2005 residential standard. I was the co-author on the Cal CTP program, which is one of the first contractor training program for advanced controls. In the state of California now, it's requirement within Title 24 that for acceptance testing that these folks actually get appropriate training on controls. We're seeing this thing move nationally now, and I think this is just a great idea, and it's really great collaboration with the contractors folks. And of course, I'm very involved with teaching undergraduates, and I have courses in innovation, design, and lighting technology for these folks. And these students go off and are leaders and doers in the lighting industry. Our sort of principal activity is demonstrations, where we take technologies, we work with our industry partners, and we put these things out into play. And this is actually one of the first large networked municipal lighting systems in the country. And here we're looking at a fully controlled, networked municipal lighting system. And we're looking at this to inform future standards, help identify new technologies, and working very closely with partners. To sort of set the stage for this a little bit, there's a lot of very aggressive policy work that's really encouraging new thinking in energy efficiency and lighting technologies. And I think key to this is the whole push for zero net energy here in California, which is really driving a lot of additional legislative and standards processes, which is sort of a very deep dive into energy efficiency. And I think the whole concept of zero net energy looks at the combination of deep energy savings and renewables, but it really requires a very deep commitment towards energy savings. And I think that adaptive lighting is one of the keys for this. A lot of this reinforces the whole greenhouse gas mitigation, and AB 32 is sort of one of the leading pieces of legislation driving a lot of the efforts that we're doing, and we sort of are very much subservient to these kinds of directives, and looking at, you know, how do we achieve this kind of very large reduction in greenhouse gas by reducing energy use, which reduces our demand on fossil fuels. This is kind of climate legislation has driven a lot of additional kinds of legislative activity, and I think there's three key ones that I think are very important in the whole adaptive lighting arena. And this comes from the Huffman Bill, AB 1109, which looks at very, very significant game changer types of activities. And residential, we're looking at 50% lighting energy savings, indoor commercial 25%, outdoor lighting 25%. So this is really driving a lot of new technology, a lot of new design practices, and I think that really provides the foundation for a lot of our adaptive lighting work. And I use this as kind of my metaphor here, is that this is actually was at the UC Davis campus, and this is a slide of one of the largest exterior parking lots in the UC system in California, and you can sort of see this whole large array of HPS. There's actually no cars in this picture, so this is really was one of our starting points when we went back to the industry and said, let's start an adaptive lighting initiative here in California, and let's use this as our laboratory. And the whole concept of waste and being able to integrate advanced control systems and new solid state technology, marry these things together in order to really address this kind of egregious, you know, waste of energy. So there was a very strong interest in focusing in on this. I want to sort of underwrite this and sort of show you a series of illustrations that really shows that adaptive lighting is one of the larger you know, energy efficiency opportunities. And this is this kind of scene that I'm showing here of this kind of middle of the night massive kind of parking lot, completely unused but fully illuminated, really illustrates the importance of this. So these series of slides really sort of shows this whole issue. We're very engaged in Prop 39 right now, which is looking at relighting schools, and the big focus here is relighting school parking lots with adaptive lighting. And this kind of situation where you have a completely empty, unused parking lot within the sort of the educational facilities, quite commonplace. This is a typical campus building, which really shows as a metaphor the adaptive lighting, that, you know, we have all the pathway lighting, all the street lighting, all the area lighting, all the stairwell lighting, fully illuminated, and no one's there. And so here's a sort of a prime example where adaptive lighting, using lighting appropriately, using integrating sensors, could be a very large energy saver. Again, showing sort of the combination of an empty stairwell, well illuminated, lots of daylight, certainly adaptive lighting here where we could integrate both vacancy, occupancy, and daylighting bi-level controls would be a very large savings. These kinds of examples surround us. We've got sort of full daylight and lights are on. And so these kinds of things are commonplace in the fabric of how we illuminate our buildings. This is kind of wasteful behavior where simple adaptive lighting using vacancy, occupancy, daylighting, tuning strategies could save us an enormous amount of energy. This was kind of a whole integration of advanced technology here, yet we didn't go to the next step with the adaptive capabilities. And so we relit here in this kind of application, but here this building is unoccupied, it's more than enough daylight. We could have integrated adaptive lighting. So the whole concept of adaptive lighting is marrying some of these new solid state technologies with controls, and that sort of the myopic, LED solution alone is not enough. So this is kind of a nice illustration showing the pathway lighting, lots of daylight, no one's there. So this is an ideal application for how can we use adaptive sensing here to reduce the light during these periods of waste. Again, sort of parking lots. And I use these slides to really illustrate that this kind of problem is commonplace. This is sort of one of the really big issues in these parking garages that are illuminated 24/7. And here we have 6 cars in this parking lot, and there's more insightful ways of addressing the issue of energy efficiency here with adaptive lighting solutions. And so I think that these really are prime candidates for these kinds of next generation solutions. Here, there wasn't any cars in this parking structure here, so an ideal kind of application for this kind of. Now, adaptive lighting is not just an exterior lighting issue. I think the whole concept of egress and wayfinding and hallways and stairwells inside institutional and commercial buildings, this is an ideal application for bi-level or adaptive lighting principles where we can dynamically adjust the lighting according to need. And so this is kind of the fundamental thesis behind adaptive lighting. Certainly stairwells are an enormous opportunity for energy savings using this kind of adaptive lighting kind of approach. So to get into some of the kinds of experimental work, we really looked at adaptive lighting as an opportunity to save very, very large amounts of energy. We're looking at 50% savings opportunities. And I've been using the state agencies and state campuses and municipalities here in California as my laboratory for really focusing in on these kinds of opportunities. And I'm going to talk about some of the demonstrations that we've been doing across the state here at the different campuses in the adaptive lighting arena. One of the first things that we do with our partners and with our demonstrations is really find out where is our energy being used. And these kinds of energy use profiles are very useful for developing and targeting efficiency opportunities. And what I'm showing in this pie diagram, if you look, there's exterior building, there's exterior parking pathway, corridors, bathrooms, mechanical spaces, stairwells, and about half of the lighting energy use pie for a typical institutional building is ideally set up for using bi-level vacancy, occupancy, adaptive lighting principles. So it's really something which is an ideal opportunity for using these kinds of sensor control approaches. So I use these kinds of energy maps to help sort of guide a lot of our retrofit programs. And so really looking at the opportunity here of using bi-level adaptive lighting to save 50%, and really it's adaptive lighting in these retrofit applications is a tremendous opportunity. I've got kind of this list of 10 strategies, and these are sort of the standard strategies that we use in commercial and institutional buildings that have been routinely demonstrated to save 50%, and they're all basically adaptive lighting. And the idea here is that the lighting changes according to need. And what I'm going to do is I'm going to focus in on a number of these things relative to the exterior lighting portfolio. I wanted to say that the history of this really grew out of some of our earlier work on using adaptive sensing or sensor technologies inside buildings, where we use relatively simple sensor technologies to dynamically adjust the lighting according to presence or according to need. And a lot of the early work that we did with bathrooms using sensors, and we were able to integrate this into the 2005 Title 24 requirement for residential bathrooms. And what we found was, which was pretty obvious, was that it was lamps that were being left on longer than 1 hour, where this was 75% of the energy. The common use patterns, of course, occurring in the 1-2 minute region, but really the bulk of the energy is that most of the energy was in an hour or longer. So we got very engaged in bridging this into other applications like stairwells, and stairwells were 24/7 in a lot of these commercial spaces, and this was sort of the first real sort of application of bi-level technology, what we really focused in on. And the idea here is the lamps would go from 100% to 50% on vacancy. So we got a number of our industry partners together, and we did a whole series of demonstrations, and we were able to integrate sensors, not that turned the lamps off, but just took it to 50%. So here the idea was that fixtures had onboard sensor technologies that would take the lamps from 100 to 50%. And this was sort of one of our first adventures into this adaptive lighting, and not turning the lamps off, but just turning them down. And here is sort of deep, sort of the integration of passive infrared devices on solid state technology. This is now being commercialized, and we have many applications throughout the CSU and the California State Universities and University of California. We've redone all of our stairwells with this bi-level technology. This was a large demonstration that we did at UCLA, where we retrofitted the stairwells with bi-level technology. And again, the concept here is as you go into the stairwell will go up to 100%, and then will return down to a lower level, 25 or 30%, whereas before it was at this static level of 100%. So we typically get very large savings for this. This is about 50% savings with this. And again, we use this adaptive lighting kind of concept in stairwells and in corridors, and it really helped inform our work for exterior applications. This is kind of hard to read, but I really wanted to sort of show this kind of common thing that we see in a lot of these applications, was that the actual occupancy rate inside these spaces is very low. You're looking at 10, 15% occupancy, and it really illustrates the idea that bi-level, being able to use adaptive controls to take the light down to a lower level during periods of inactivity. We found that corridors were one of the larger energy-saving opportunities, and again, this kind of concept of bi-level, with the idea that we could use occupancy control or adaptive control to bring the lights down to a lower level. And again, corridors was kind of a large opportunity for saving energy. But this whole process of adaptive bi-level lighting in corridors and stairwells really helped inform us on the exterior application. And here again, it was relatively simple integration of either passive infrared or ultrasonic technologies. The nice thing on retrofits is corridors are typically on the same single circuit, so it was a very good kind of retrofit. And here are students working on these kinds of systems. This is one of the first adaptive corridors. Again, we partnered very closely with the fixture industry and the controls industry and developed a whole series of demonstrations. We did this across the state. And this is the kind of data that we typically get in these adaptive lighting applications, where this is showing sort of a typical day. And then you get this sort of on to 100%, down to 50%, and then at 50% all night, and then on during the day. And then these are all people leaving work. And then weekend applications showing this someone's coming into the office, and then it's returning to 50% all day. So this kind of data was very standard for many of the corridors. And again, adaptive bi-level lighting, very successful in corridor applications. We did a big study at the University of California at Santa Barbara. And again, the idea of adaptive lighting we were showing very low occupancy in this campus, 10% of the corridors being occupied at any point in time. So it really illustrated the importance for this. And of course, this got integrated into the 2013 Title 24, and just July 1st this year, as this is effective now for stairwells and corridors, must use some type of adaptive lighting, sensor-based controls. And so this was very successful in terms of integrating into best practices. And actually, we're seeing this kind of activity now in inside grocery stores, and we partnered with Sacramento Municipal Utility District, and we integrated adaptive controls on now Target and Walmart is now doing this. So this kind of adaptive lighting exercise that we did with corridors and stairwells really helped inform us to this whole process of integrating controls, bi-level controls in exterior lighting applications. And again, this was we worked very closely with these folks, and there was very strong interest from the legislative types that we really need to engage in deeper energy saving opportunities for exterior lighting. So again, we took the same kind of principle here where we could use strategically located sensors to make decisions on bringing the lamps from 50% to 100% during periods of occupancy or traffic or pedestrians. And so these were some of the first exercises that we did with looking at mesh networks and RF controls. But we started very early with fairly simple passive infrared detectors, and we integrated fixture-based controls with the idea that fixtures would each have its own individual level of control, providing localized, sensor-based bi-level. The fixture at the right here is actually a fully networked fixture that does the passive infrared plus wireless communication for a larger network, and I'm going to get into that a little bit further. But this was sort of our first kind of experimental efforts where we took fixture geometries and we integrated relatively simple passive infrared detectors, taking this fixture from 50% to 100 and then back down to 50. We did a lot of deployments with this, and this is actually showing a PV canopy, and again, consistent with the whole zero net energy, the idea of solar integrated with bi-level lighting systems. And so there was a natural partnership on this, and we've done a lot of demonstrations on this, and it's now we've developed before the Title 24, we've actually developed a specification now for PV canopies. And so moving forward now, the UCs and CSUs are using this bi-level adaptive canopy specification. And the basic specification we have now is that all PV canopies shall employ bi-level adaptive lighting. And this is consistent with Title 24 130.2. A lot of experimental work where we've gone into parking garages, and again here showing the repainting of garages to get a better distribution of flux. Each one of these fixtures has got an onboard control system, again bi-level. Very engaged with the UC system and CSU system, and now most parking garages across the state within the university system have converted over to adaptive bi-level, and we're getting fairly significant savings on this. This is kind of a no-brainer for parking structures. This is the kind of data that we typically get in these kinds of applications, and this particular fixture was designed to go to about 30%. Here I'm showing at midnight it's up at 100%, and then during periods of vacancy it retires. Adaptive lighting retires it down. Here's somebody driving through the parking garage at about 4 in the morning, and then it's back down to 50. And then the parking garage is on all day, as it should be, because people are driving through. And these are all people leaving or escaping from work, and the lamps are going on and off throughout the day. And the old system, this was HPS. So we went from HPS to bi-level LED. And so typically getting 60, 70% savings on this kind of application. Data depends on application, and so we're doing hospitals, we're doing schools, we're doing universities, we're doing private buildings, and the data profile is different, always depending upon the nature of the occupancy. This is actually a hospital, and so fairly large savings, but again, the use dynamics in terms of the adaptive lighting is very different. This was actually one of the first bi-level parking structures that we did, and we partnered with the industry on this, and this is actually at 50% light. The idea was we worked very closely with the safety people and the police folks, because the whole idea of turning off lights in an exterior environment was quite threatening initially. But what we found was that with the sensor controls, going from 50 to 100%, was actually a welcoming experience, and we did a lot of interviews, we did a lot of surveys, and we found that people are actually very comfortable with this. So we worked very closely with the safety and police departments on sort of the initial phases of this. It's actually a close-up view showing the LED fixture with the adaptive controls, and so now most of our industry partners have a line of fixture products that include adaptive controls. If you have a parking structure integrating LED and adaptive controls, just makes sense. We just finished all of the parking structures here at UC Davis and also at UC Irvine and also at UC San Francisco. We're getting an average campus-wide savings of 71% campus-wide. With the integration of kind of this adaptive lighting approach. So it's certainly a large energy saver. The whole codes and standards process now, the way this reads in Title 24 is that all luminaires mounted between 12 and 24 feet above the ground shall be controlled with motion sensors. And so this kind of adaptive lighting is now wired as a best practice within Title 24. So this whole adaptive lighting for parking structures, it's included in Title 24. That we have broad utility programs now in the state. Parts of this have been carried over into ASHRAE, and some of the partners here in California are working very closely with ASHRAE. We have broad inclusion at all the campuses. The campuses have embraced this as standard practice now for parking structures. The state invested in this very heavily with the ARI money, and we have very strong industry support on this. And this was something that we partnered very closely with the manufacturers on, and we moved this forward as a standard, as kind of a collaborative effort with the lighting industry. We're now starting to focus in on wayfinding and pathway lighting, and this was sort of an application of how do we do this in a network type of approach. So what we've been exploring is the idea of local, regional, and area-wide integration. So I want to sort of talk about adaptive controls in these kinds of environments where pathway lighting becomes adaptive relative to pedestrians and bicyclists. And we're using this kind of activity to help inform our roadway lighting kinds of applications. And what I'm showing here is a typical pathway kind of system with local controls here. This is passive infrared that looks up and then looks down the pathway. And if you look closely here, you'll see a small little antenna. And this is an antenna that gives us sibling control. So the idea here is, it's sort of a close-up, is that this makes local decisions, turns the lamp from 50 to 100%, and then we get RF communication from pole to pole. So here there's a local decision that is made that takes us from 50 to 100. It then sends a signal to its siblings to bring this up. We can program this to bring up 1 or 2 or 3 or bring up the whole road. We also have the ability to communicate back to home base It can also take a local demand response signal. So we're doing a lot of experimental work now trying to understand how many siblings need to be controlled depending upon how fast traffic is going. And so, and again, we've got sort of a lot of pathway average kind of occupancy in the 40% region, so with the tremendous opportunity to save energy with these kinds of controls. We have a fairly large-scale deployment of this, and we've this is actually the football field pathway. And so what we've done is we've loaded all of these pathways here with devices to measure, and we've been getting 60% savings here in these kinds of pathway applications. And here I'm showing the fixture going from a low level up to a high level on detection, and then back down to a lower level, and then of course off during the day. So this kind of adaptive lighting is giving us about 60% savings. Now we're using a lot of this pathway lighting to help inform some of the street lighting applications, where we use this kind of sibling control, where we make decisions at one place and then we broadcast the signal down. And so we're looking at this with the idea that it could help inform some of the activities. And we're working with the City of Davis now on this networked control system. And the idea here is that at this plane, we detect motion either with a pedestrian, bicycle, car, motorcycle, and then it sends signals down to siblings to come up to 100%. And so we've had a lot of success with this on different roadways. And again, the light's at 50%. We then RF to bring everything else up to 100. So this has been quite successful. This is actually showing a close-up of this. This is a passive infrared device that makes local decisions here. We actually, a lot of the experimental work that we've done at different campuses, we're getting 100% detection at the pole, and then we're controlling with RF down to siblings. We're also taking demand response signals and also scheduling signals back to home base. So this is showing some of the retrofits that we're doing with this kind of approach, showing the fixture and the RF control device and the wiring of the passive infrared. You can actually see there's a lot of different experimental activity going on relative to how do we detect this. Now we're using passive infrared, we're using ultrasonic devices, we're using microwave devices, we're using devices in the roadway, all kinds of different techniques that will essentially tell the fixture to go to 100% and to send a programmed signal to siblings. This is actually a map of the UC Davis campus, and every one of these little red points indicates a networked sensor-based RF control point. And again, this is a large working laboratory, and we're really finding out that, different parts of campus have different kinds of control needs, and we're really looking at trying to understand, sort of major roadways like this, how many siblings do we need to communicate with versus, something more dense like in this parking area here, we may not need the same level of controls. So we're working with our industrial partners now, trying to really find out, what level of granularity, but also what level of adaptive controls can we do from home base. And so what we're doing now is we're finding out that certain parts of the city or certain parts of the campus can be dialed back either seasonally or weekly, and we can send an RF signal out to a certain part of the city to say, look, these fixtures can be at 10% for the next 3 days. And so we're learning an awful lot about this right now in terms of what the future campus or future city can be. And we have this kind of future cities initiative where we're really looking at how can municipalities best exploit this kind of activity. This is sort of showing some of the future stuff that we're doing with adaptive controls on wall packs. And wall packs are tremendous opportunities. There are long hours of use on this. So simple adaptive lighting on wall packs is a very large energy saver, actually part of our schools program. we're looking at the integration of bi-level wall pack systems. And these kinds of wall packs, again, typical occupancy, 20% of the time there's actually somebody in this region. And we're getting 70, 80% savings in wall pack areas. Now, the future vision on this, the kinds of things that we're looking at in adaptive lighting is that certainly the vacancy occupancy is well wired into best practices. We have Title 24 reinforcing this and parts of ASHRAE coming up. But we're looking now at future opportunities on scheduling and communication. We're finding out that certain parts of the city can be dialed up or dialed down, or can be event-driven. We're getting a lot of interest in using advanced communications for scheduling. Also, maintenance needs. If this fixture fails, it can send a signal back to home base that something has happened. We're getting a lot of interest from our industry partners on this. Perhaps some of the big drivers in adaptive lighting, we think, are going to be in the energy use monitoring and the demand response area, where we can report on a minute-by-minute or an hour-by-hour, how much energy is being used by any particular kind of fixture. And this is going to be very valuable information in the future when we get into real-time pricing and also into real-time attribution. Attribution for utility programs is going to be driven more by actual energy savings. And so we're really looking at the idea of how can we use real reporting from these systems. Also, demand response. We now have the ability with this adaptive lighting network structure to be able to send a signal to these wall packs to dial down 10% during a power event. So we're very engaged in sort of this demand response testing now with our municipal partners. Very engaged in training. We're doing a lot of municipal training now, and we're working with cities on the integration of adaptive lighting in schools and in public properties, and sort of moving forward on this. One of the key areas that we found with our utility partners, that a lot of this adaptive lighting, we were seeing a lot of failures in the field. And the failures in the field were we thought initially were happening because of failures in the technology. And what we found was that many of these failures were due to installation errors. In other words, people weren't wiring these correctly, or they weren't calibrating them, or they weren't commissioning them appropriately. And so we partnered with our utilities and with the Contractors Association, with NECA and IBEW, and we developed this whole process of training contractors on how to integrate controls inside, adaptive controls inside buildings. And so we had very close collaboration with the Contractors Association. And today, there's an acceptance testing requirement in Title 24. So if a building uses adaptive controls, there needs to be a walk through the building by someone who's actually studied lighting controls and has taken this advanced acceptance training program. And so we see great opportunities on accelerating adaptive controls into buildings through this kind of educational process. And this has been very successful. We have really wide attendance on this. It's very well embraced by the Contractors Association. Loves this program. And we have a lot of very close collaboration and support on this. I wanted to sort of finish up on this in terms of where I see adaptive controls going, and this is kind of, I think, partially a vision forward. This is the Honda House at UC Davis, and this is a zero net energy house, but it also incorporates some circadian rhythm kinds of approaches for adaptive lighting. And again, this addresses both the visual pathways, but also the biological pathways for lighting, and how can we change or adapt lighting according to our biological needs. And this addresses the whole issue of both dark adaptation and bleaching of rhodopsin, but also the disruption of our melanopsin receptor and with the idea of trying to reduce the amount of blue light at night. And this really speaks to the whole concept of adaptive lighting and being able to change. And so we're looking at, and this is all experimental, looking at how do we change light on a diurnal basis. And there's lots of activity going on in this, and this is sort of showing some folks that are doing work on corridor lighting, and throughout the day you've got bright white light so that you have high light levels for moving up and down the corridor, but in the evening retiring to a red amber, which is going to present less disruption on our circadian rhythm and potentially maintain our dark adaptation. And we're exploring this a lot with it. We did a lot of work in the about 15 years ago looking at healthcare facilities and integrating amber lighting inside healthcare facilities, and now we're looking at this in residential applications with the idea that in the middle of the night that the lighting would adapt to both a lower light level, producing a lot less blue light, and have amber red, which would help preserve dark adaptation. So we're doing a lot of work with our builder partners, integrating this low-level red amber LED. This is a view inside the Honda house, and again, it's kind of a future-forward view to adaptive lighting. Here, the lighting adapts to a much lower light level. There's a shift towards the red amber. Low light level preserves dark adaptation and doesn't disrupt the melanopsin receptor. And we're using this on stairwells and hallways as a kind of an adaptive lighting approach. So one of my students doing experimental work on different amber systems. So I think that there's this whole idea that lighting can adapt, can change, and so we've seen a large move to solid state lighting systems for exterior lighting at high color temperatures, but I think we're going to see a progressive move to lower color temperatures, and potentially the idea that lighting will change, will adapt on a diurnal basis to lower color temperatures at night to be less disruptive. Now, there's a lot of, this last slide is, I want to sort of direct you to our website. We've got lots of technical follow-up information. There's the codes and standards processes. There's a lot of our demonstration sites. There's a lot of technical information on specific manufacturers that we're working with. Lots of information from our demos. And so please feel free to follow up. This information you can download for free, and it's available for more follow-up. So Nathan, I'm going to turn this back to you.
Thank you, Michael. That was a wonderful presentation. I'm sure I speak for the rest of the people attending that was actually very informative. Ladies and gentlemen, I'd like to direct your attention to the screen for what we have coming up in November. We have a live webinar on the benefits of indoor positioning. So this is about supermarket lighting, on using the light to have the best effect on the product, as well as using the light to guide your shoppers throughout the supermarket. And on November 12th, we have a live event, the Luminous Talks live event. This event will be hosted live, so on location in New York, but there will also be a live stream. So please be sure to sign up for that and check our homepage for more information.